Simulation is going to be fun, but it requires the use of a computer. I don't really expect you to be doing it like I didn't expect you to do statistical computing with the computer, but I want you to understand how it's done, why it's done, so that you'll have an understanding of it and a feel for it. Let's say you had an assignment in a class, and the assignment was to obtain 1,000 averages of 100 observations each from a uniform distribution on the unit interval 0, 1, and then plot the averages on a graph. All right, let's get the picture. 100 averages. In each of the 1,000 averages. In each of these averages, there's 100 observations from a uniform distribution. Uniform 0, 1 distribution. And then take those 1,000 averages and plot them on a graph. Okay, that's the assignment. How can we do it? Well, let's just be naive and do it. We could construct a dial, mark it from 0 to 1. Now, let me draw this. Here's a dial. Mark this 0 and 1, and this 0.5, and this 0.25, and this 0.75, and mark the other numbers in between like that. Put a dial here and spin it. If we do that, and it's a uniform dial, then the numbers we get will be uniformly distributed from 0 to 1. If we spin the pointer 100 times, we get ourselves and average it. We can have an average of 100 uniform 0, 1 numbers. So that doesn't sound too hard. Construct a dial, spin it 100 times, and take an average of those 100 numbers. But then we would have to repeat this whole thing 1,000 times. We don't have to rebuild the dial, but we do have to spin it 100 times, 1,000 times. Okay, then we have 1,000 averages. And then we could graph the results. That wouldn't be too hard, sitting there one step after another, putting 1,000 little marks on the page. Okay, we could do that. I wouldn't recommend it. It would take probably, well, a lot longer than you care to do. You might be a much older person when you get done. So that's not the way I would recommend doing it. We could do it that way, or we could simulate. Now, I'm going to show you how I would do it if I were given this assignment. I go into Minitab, and I'd say, okay, Minitab, rand 100 C1. That means take 100 random numbers and put it into C1, coming from, subcommand, coming from the uniform distribution 0, 1. So that will put 100 uniform 0, 1 random numbers into C1. So I've got a column C1 with a bunch of numbers, 100 numbers in it from the uniform distribution I want. I then say, let K1 be the mean of C1. Well, that gives me X bar. That gives me X bar, the average. I say, set C2 with K1. So in C2, I put X1 bar, the first average. I put that in C2. End my data, and I'm finished. Well, I've done that once. I've only got one average in here. It took maybe a minute. That's a lot quicker than spinning a dial 100 times. But I need 1,000 of them. Okay, I don't care. You want 1,000? I'll give you 1,000. Here's what I do next. I say store. Actually, when you say store and give a name, you are doing what's called creating a macro. A macro. A macro is a set of commands which is going to be executed later. It's not executed when you write them. They're just stored in memory to be executed later. And you see the word store here. That means it's storing all these commands in memory in a file called project. So when I call project, it's going to execute these commands. Okay, so what I want you to do, I'm saying, okay, rand 100 variables, put it in C1 from the uniform distribution. So I'm telling it to make a C1, put in 100 numbers. I'm telling it to take the average, let K1 be the average, the mean of these, find X bar, insert after C2. Well, C2 already has in it X1 bar. I'm going to tell it to take the average it just found and put it after it. That'll be X2 bar. Okay? And that's all. But it doesn't do that. I'm telling it to do it, but I'm not telling it yet. I'm just saying these are the commands that I'm going to ask you to do later. And I've stored it in a thing called project. And now I say execute project 999 times. So what does it do? It generates 100 random numbers, finds the distribution, finds the mean of them, inserts the mean after where it was before. That puts x2 in there. And now it does, that's one down. Let's go another one. Does it again. That gives me x3. Again, x4. It does it 999 more times. I already had one in there. So the final one is x bar 1000. X bar 1000. I got 1000. X bar 1000. I've got 1000 random numbers in there now. Now I can take these numbers and plot them. Well, I certainly am not going to plot 1000 numbers by hand. Not when I have a computer at my disposal. I say dot plot the data in C2. And it makes a dot plot. What does that dot plot look like? It's really no surprise to us. Averages are bell-shaped. They're centered around 0.5, which is the expectation of a uniform 0, 1. If you have uniform 0, 1, the center of that is 0.5. So it's centered around 0.5, and it's bell-shaped, and its standard deviation is approximately here, right? What's that? Maybe 0.53. So from 0.5 to 0.53, the standard deviation sigma is approximately 0.03, right? So we can look at this and we can see what the mean is, what the standard deviation is, and the fact that it's normal. And it didn't take any time at all. It took us a couple of minutes while we were waiting for this macro to execute 999 times. We went out and got a cup of coffee. We didn't have to sit there and watch it. It'll take as long as it takes us to drink a cup of coffee for it to do that. It's doing it very slowly. Well, very slowly. Compared to how we would do it by hand, it's hardly very slowly. Okay? That's simulation. That's what's done. What simulation does is create a universe inside the computer. And then that computer creates data. And that data looks like real data. That is, it comes from the same distributions as real data. After all, what is an experiment? In an experiment, you get some data. You take a book and you measure it. The book has a true mean, and there's a distribution about that mean with a standard deviation, and we say that's, normal data. So we could say in the computer, give me 10 readings on something with mean 9 and standard deviation 0.02, and it would give me 9 readings, and then we can see what properties go on with those readings, just as we would do in real life. Of course, it wouldn't give us the mean we know is 9. We don't have to estimate it, but it would tell us how good our estimating procedures are, how accurate they are. If we do something, we know the answer is 9, and we do something and it says 10, we say, wait a minute. If we did something with a book and it said 10, someone had a new measurement and they got 10, we'd say, well, I guess the book's around 10. There'd be no way we'd know. But if in the computer, we know the length of the book because we put that in. We're the gods in the computer. We know what the parameters are. We told the computer how to generate the data from the parameters. And so we can look back and say, hey, did it do it right or did it do it wrong? That's what simulation is all about. Okay, the computer finds the average of the simulated data. Now, it doesn't really have to be the average. If it were if you were interested in medians, it could find the median of the simulated data. It could find the standard deviation of the simulated data. It can do anything you want, and it will do this using a large amount of data. And therefore, it will have a very good idea of what the true value is. Now, let me say this. Simulation is used when we are interested in the properties of a statistic which we can't find by direct means. There's a lot of people who don't trust the computer and say, well, why are you using the computer? And I will tell you, use it when you can't find something by direct means. For instance, let's say I have a fair coin, and someone says, what is the long-run average in a game where you flip the coin, heads, you win $1, tails, you lose $1? What's the long-run average? Well, I could actually sit there and play the game for a few thousand times and find out how, after 1,000 flips, let's say, how much did I win or lose, and take that number and divide by 1,000, and that would be my estimate of my winning or losing, my long-run average. It would come out pretty close to 0. I wouldn't win or lose too much in this game, and if I divide by 1,000, it comes out a pretty small number. So I would be estimating, I'd say, oh, 2 cents is the average for this game. I could also simulate. I could generate 1,000, 10,000 numbers, say, get me 10,000 numbers, probability of 1 is a half, probability of minus 1 is a half. So give me 10,000 ones and minus ones with probability a half each, and then average them up. And that would be the long-run average for 10,000. Simulation could do it pretty quickly. However, I don't recommend doing that, because we might end up with 0.001. That would be the simulated average, and it wouldn't be as good as saying, hey, probability is a half since it's a symmetric coin, and 1/2 times plus 1 minus 1/2 minus 1 times a half gives me 0. The expectation or long-run average of that game is 0, right on the button. So I can do it exactly. I can do it actually exactly, know exactly what the answer is. It doesn't make any sense to simulate. It doesn't make any sense to get long-run averages. I can figure the answer out. So I don't simulate when I can get an answer directly. However, there are many times when you can't get answers directly, and you want to simulate so that you can have an answer. You won't have an answer if you don't simulate. With a large amount of data, properties are easily determined. See, I can find the properties of a statistic when I have a lot of data. We said the reason we can't find the mean is because it's the center of an infinite amount of data. Well, we don't have an infinite amount of data. We only have 20 or 30. But in the computer, I can have 100,000 or even 1,000,000. Now, 1,000,000 is pretty long run. And with 1,000,000, I can get to 3 or 4 decimal places, and that's probably good enough. And I essentially will have the center pretty close to it with a lot of data. So using simulation, large amounts of data are easily obtained, and with large amounts of data, I know that I can get the results I want. Okay? So simulation is used when you can't do something directly, and you want to do an experiment, but you don't really want to do the experiment. You don't want to flip the coin 100,000 times. You don't want to, you just don't want to do something that you can do inside the computer's world, because it can do it in a fraction of a second, and much quicker and much better than you can. And why not let it do it and analyze its results? And that's what's done in simulation, a very powerful tool to statisticians. And I just want you to understand it, and if you can use it, but it's not one of those things I really expect you to be using. Okay? Hope you learned something.